So the physics problem we have is a boy sitting on the edge of a 20-meter tall cliff tosses a baseball at an angle of 78 degrees into the air at 25 meters per second. At a certain point during the ball's flight, a driver of a car that just finished pumping gas at a station 90 meters away from the edge of the cliff decides to gun the car towards the cliff at a constant acceleration of 4 meters per second squared. The ball hits the roof of the car, 1.53 meters in height. At what distance from the cliff did the two collide? How long did the car wait before it was gunned towards the cliff? So with this information, we can draw a diagram to better visualize all the parts we are given in the initial problem. The cliff is 20 meters tall, so I'm just going to fill that in. The car is 1.53 meters tall. The ball's initial total velocity is 25 meters per second, and the boy throws the ball at an angle of 78 degrees. Knowing the speed at which the boy initially threw the ball, we can simply find both the initial vertical and initial horizontal velocities of the ball at this moment by creating a right triangle. So here I've made a triangle with 25 meters per second as the hypotenuse and 78 degrees as the angle. And now I can break up the legs of the triangle to stand for the vertical, also known as y, and horizontal, also known as x, components of the velocity vector. So for this, we're simply going to want to use SOHCAHTOA, and to find the vertical component of the velocity, we can use sine 78 equals y over 25, and this will give you the leg opposite the given angle, and that turns out to be 24.45 meters per second. And the same thing can be used to find the horizontal component, which is x in this case, of the triangle, using cosine, which calculates to be 5.20 meters per second. So that's the horizontal velocity initially. So right now we can just add this to our diagram to keep track of all the info. And we also know the final vertical velocity of the ball at the height of the cliff the second time, because it is known to be the opposite of the initial value, considering the ball's path is a symmetrical parabola. So if it's 24.45 initial velocity vertically, then at the second time that it hits the height of the cliff, then it'll be the same value, 24.45, except negative. So this problem can be solved using different methods, but I will be just separating it into two smaller sections, one being where the ball is above the height of the cliff, and the other one being once it falls beneath the height of the cliff. So now to start, I prefer starting with finding time, since time doesn't change depending on whether we're using anything to do with horizontal or vertical components, but it's the same for both. So it will be very helpful for our displacement equations and other calculations to come. Using this, we can find the total time of the ball's flight until it reaches the same height at which it started. The acceleration equation can actually be manipulated to find time, so we can change it to time equals final velocity minus initial velocity all over acceleration. So using the vertical path of the ball and the info we got from that, we can create the equation negative 24.45 meters per second minus 24.45 meters per second all over negative 9.8 meters per second squared, since all vertical acceleration of objects in free fall is negative 9.8 meters per second squared. So we can just use unit analysis here to cancel out the units, and we find this value to be approximately 4.99 seconds. So again, we just use this to fill in our diagram. Now, if we want to find the time it takes for the ball to go from that point that we just looked at the cliff's height, to the roof of the car, we first need to calculate the height the ball must fall in order to collide with the roof of the car. Since we know the cliff is 20 meters high and the car is 1.53 meters tall, we can subtract the height of the car from the height of the cliff to find the height the ball must fall from the top of the cliff the second time to the roof of the car. It sounds confusing, but if you look at the diagram, it's pretty simple, and it becomes 20 meters minus 1.53 meters, and it yields 18.47 meters as how far the ball must fall. Knowing this, we can find the time it takes for the ball to fall this vertical distance. Using the displacement equation, we can fill in the displacement as negative 18.47 meters, which is what you just found, except negative because the ball is falling beneath its initial point. The initial velocity as negative 24.45 meters per second, and the acceleration as negative 9.8